Okay, so there's basically two attitudes. Let me zoom in a little bit. Two attitudes in computer science. One is this is what most people think. Math doesn't matter because computers get faster, so it's irrelevant to try to optimize code using math. And let me change the settings so this wraps real quick, like soft wraps. Hold on just a second. Edit.
What's this?
Thank you.
Yeah.
Window tools, settings, preferences. Sorry, silly bar cuts in the way all the time. Oh. One example, actually, by the way, let me just point this out real quick. Do you see on the screen how it says end of line? It's carriage return line feed. Did you know that probably wastes about $6 billion a year that they actually still use carriage returns, which come from typewriters like back in the 1970s, as well as line feeds to go to the next line. Because if you have a typewriter, when you go to the next line on your page that you're typing, you can actually just scroll the wheel down and go down right into the middle of the next line. So you have to do a carriage return, go back to the beginning, as well as a line feed to go to the next line. But with computers, it's impossible. You can't just you can't push return and go like you can't push return and like go from that point and then suddenly jump to like this point on the next line because there's no characters that have been typed before that point on that line. So it's basically just one dimensional instead of two dimensional. But um, some computer systems have carriage returns and line feeds. All the modern computer systems got rid of them back in like the early 80s. But there's still some computer systems, like Windows even, for example, still uses both. And so how many lines of text do you think there are in the whole world at this point, do you think? Probably just billions times billions times billions, right? And every single time that you have like a web request through the internet, there's like maybe 7 or 10 different lines of HTTP headers and so on and so forth. So every single one of those has like twice as many characters as needed at the end of every line. Um, even if you calculate that only takes like 1% of 1% of the energy and storage and bandwidth to transfer those extra little characters, it still adds up to billions and billions of electrical energy and everything like that. Just because they didn't care about optimizing it. Let's see. So they're literally still sending typewriter instructions through the computer systems nowadays. Um, okay, let's see. It only takes me like 5 seconds to find this usually, but highlighting. Um, Toolbar. Wrap. Okay, let's see. New document. Indentation. Auto analysis, none on that. Highlighting. Current searching back. Well, maybe the view. Maybe it's under view. Word wrap. Maybe that's it. Oh yeah, there we go. Okay, so not even in the preferences. Okay, so that's one attitude is the math doesn't matter. And many people actually, probably most programmers feel that way. In fact, I was actually talking to another professor one time a while ago. He's not here anymore, but um, he would and I just said, well, you could do this if you wanted to, and it would let you like find a random element of a database and like only using like maybe 1 millionth as much memory. And this professor said, well, it doesn't matter because computers have enough memory anyway, so that doesn't really matter. And I was saying to myself, well, what if you were searching through the database of like Facebook? There's no way that you can put the whole information of all billion people in the whole world into the memory of one computer and do it that way. So let's go ahead, and the other attitude is math does matter, and it's worth learning, and it's worth the 1% extra effort to go 2 million or more times faster. Now, I don't know for sure if this is going to go 2 million or more times faster today, but we'll find out. So I'm going to type this all up as HTML. So this is like a little HTML review. How many of you have ever done any HTML before? Perfect. Okay, good job, everybody. So and when you're using Notepad plus plus to edit with, you can actually just push F5. Well, maybe you have to configure it actually, but okay, let's just save this document. Let's put it on the desktop and let's just save this as HTML stuff 9/10/2025. And I'm going to let you have this file, but then I'm going to make you change one thing in the file on your own for your homework assignment. So make sure you follow along and understand what everything does so that you'll know how to change it. Wow, why don't they have... Oh, well, it doesn't even matter. I'm just going to do... As long as I have the extension, it should still work fine. Okay, so there's that. Now I'm going to open that file with Chrome. So hopefully it'll open. So desktop. Yep, right there. So here is the code. Here's the information that we typed. Let me put that on the right side of the screen, and I'll put the code on the left side. So let's zoom in a little bit on that. Now, by the way, let me teach you a little bit of code that you might not know. So if you want to have pre-formatted text in HTML, you can put it in the pre tag, right? But it preserves white space. That's what pre stands for. But you can also actually change it, the kind of white space to be pre-wrap. That preserves the white space, but it wraps the text though. So let me reload that. Now, boom, look at that. So it preserves all the white space and the line feeds and everything that I type, but it lets the text wrap to the size of the screen, which most people would want unless they don't want it to wrap at all. So there's that. Now I'm going to start typing some code and I'm going to explain what all the code does. And this is coming from the book. I mean, the code's not coming from the book. But this is coming from the book section in chapter 2 about sequences and series. So let me explain though. So let me type a little paragraph about this. So let me go over to this part. So background of today. Let me move this out so I can type better. A long time ago, there was a class and the teacher was just a very bad teacher and they made the kids do nothing but busy work. So the teacher told the students he was busy and he didn't want to get interrupted, so he just told his class to add the numbers 1 + 2 + 3 through 100. And he said, figure out what that equals. So he told the kids to do that. And then he's like walked away. And then like 5 seconds later, one of the students comes to the front of the class and says, I know what the answer is. And he tells them the answer. And I don't think the teacher even knew, but finally the teacher realized it was the right answer. And so he was stumped or whatever. He was awestruck. So how do you think the student could have figured out the total of those numbers without actually, unless he was like a savant or something like that, in just 5 seconds? And he was only like maybe 5 years old or 6 years old or something. So think outside the box. What if I took those numbers and reversed them? Ready? What if I reversed those? 100 plus 99 plus, and let me space them out so that you can see them like this, plus 98 plus 1. Yeah, so you just realize that 1 plus 100 is 101. 2 plus 99 is also 101, and so forth. So if you don't know what this answer is, right? So this is unknown. So what letter could I use to represent unknown? X. How about, yeah, let's just say capital X, I guess. So that's X. Well, this also, do you agree, would you all agree that it makes logical sense that 100 plus 99 plus 98 plus 1 would equal the same thing as 1 plus 2 plus 3 through 100? The same numbers being added, right? So that would also equal, I hate autocomplete. It's completely stupid. If you know what you want to type, you don't need autocomplete. Okay, so there's that background of today. Let me see. Well, it's not worth turning autocomplete off. 100 plus 99. So, but you notice that every single number adds up to 101 now. That is actually 101 plus, what's 2 plus 99? That's also 101. 3 plus 98 is also 101. And every 100 plus 1 is also 101. Every single term adds up to 101. And who can tell me what? Who can tell me what 101 added together 100 times would equal? What would it equal? Yeah, or basically it'd be 100 copies of 101, which would be 10,100, right? You just add 2 zeros to the end. So this equals 10,100. So that's what this kid did in his head. He realized that because he thought outside the box.
That's not what it equals though.
That's not what it equals though. You're right. So how do you get what it actually equals though? Divided by 2, because you had 2 times as many numbers. That's both of them put together. So that's not. So what is half of 10,100? Right. 50/50. So boom. How does that sound? And that process actually works for any number of numbers, whether it's adding 1 through 100 or 1 through 50 or 1 through 40. The generalization of the process is if you wrote the same numbers backwards and wrote them underneath in another line, they would always add up to n plus 1. Every single copy of the numbers would always add up to n plus 1. And if you added both copies together, it would always be n numbers total times n plus 1 would be the total of each column. It would add up to n plus 1 times n. And if you divide it by 2, you get the correct answer. So that's the formula, is that the total of the integers 1 through n is always equal to, now the way they write it in books is like this, n times n plus 1 divided by 2. They put the n first instead of n plus 1 first. Because they didn't really think about how it worked, they just thought about they put the n first because it's like smaller. So the total of integers 1 through n is equal to n times n plus 1 divided by 2. But I would say probably the majority of people who write computer code, like literally I've seen code in like Mozilla and everything else like that does things super inefficiently. Like there's one line of code that I fixed that went 2 million times slower than it should have gone because they didn't do it the right way. So let's go ahead and oh, by the way, let me save this and reload this so that you can see it. So let me go ahead and type the code that will actually do this and see what happens. So first of all, I'll teach you a little bit of a language called JavaScript. JavaScript is the world's most widely used language because it's used inside of web pages to program like directly. It's the native language basically of HTML and web pages. So it's also used on the server side as well with a lot of different implementations of it that run on the server side as well. So let's go ahead, and I just typed this up at like 6 o'clock this morning. Just out of my head, just because I thought it'd be exciting. So let's have a race. I'll have a function called race. And this is what they call an arrow function in JavaScript. It's a really cool notation that saves a lot of time. So you could have a variable in JavaScript called anything you want to, as long as it's not a reserved word. Like, for example, the word var means variable. That's like a keyword. You can't use that word for your variable because it means variable itself. But you can use other words like race. So race equals parentheses f comma n equals greater than. That's called an arrow in JavaScript. That means that you're defining a function that accepts 2 parameters, f and n. And it's going to run a block of code. And since it's actually technically a line, I always prefer to write in my lines with a semicolon. That's because sometimes you never know for exactly why. If your JavaScript gets put through some program that wraps it or something like that, then if you don't put semicolons at the end of your line, your code won't run if it gets like wrapped or shrunk together onto one. hold on, onto one line. I think it just ran out of like fluid or something like that. Let me take a drink real quick. So we're going to declare two variables, three variables actually, time one, time two, and the variable n. Now, by the way, when you use a variable keyword in JavaScript, always use that keyword if you're having local variables. It will make them run a lot faster, and it will keep the scope of these variables within this block of code so that they won't interfere with any other variables named T1, T2, or N that are anywhere else in your program. When you're using global variables, okay, so in the history of JavaScript, they've always tried to be strict, and then they've always relaxed their strictness because people couldn't get their code to work. So variable is the original declaration of a variable in JavaScript. The more modern one is called let. Of course, the problem is you can't declare the same variable more than twice within the same code. So what would happen is people would have a line of code like this, and they'd say at the beginning of their code like variable x equals 10, and then later on, 5 years later, somebody else would have another script down below that would have the same line like variable x equals 10, and then the whole code wouldn't win because it'd throw like a compilation error. So you can now declare variables multiple times if you want to. And it won't conflict with each other, but that's kind of stupid because otherwise, what's the purpose of declaring them anyway? That's just a comment, by the way. So variable T1, T2, and N, and I mean, sorry, actually variable T1, T2, and I. How do you time something in JavaScript? You just create a new date object, and then you subtract 0 from it. This is basically also kind of like overloading it. Whenever you use a date object in the context of a subtraction and in a numerical context, it actually converts the whole date object, which contains things like the days of the week and everything like that. It just converts it into an epoch representation of the time in milliseconds since midnight on December 31st, 1969 in Greenwich Mean Time. So let's just see. So that's T1. And then we're going to say do a line of code called a for loop. How many of you have ever done a for loop before? So we're going to say for I equals 0, I is less than n, I plus plus. And then inside that block of code, we're going to do just run the function called f. That's all we're going to do. So we're going to run the function f n times. Then we're going to take the time. So time 2 is equal to a new date minus 0 as well. So that represents the milliseconds at that moment in time. Then we're going to return the average time taken. So T2 minus T1 divided by n. So that returns the average time it took to run that function. Now we're going to declare a variable called count2, which is 1 million. Now, by the way, when I use global variables like race and count2, I actually typically my style code is I don't put the word variable in front of them because of those old days in which if you did put a variable in front of them, if anybody ever used the same variable name later on, it would cause the whole program to crash. That doesn't happen anymore because they relaxed that restriction. But just out of a habit, when I use a global variable that I declare, and it actually doesn't change anything about the way it actually works. Any keyword that you assign to in the global context is still just treated as a global variable being initialized. And since they've relaxed that requirement that you don't have to put the variable in front of them anyway, they've also relaxed the requirement that you don't have to not declare them twice. If it's, I basically just opted on the side of not using a declaration in front of my global ones, but always declaring the local variables. So count2 is going to be 1 million. We're going to count to 1 million, which by the way, computer programs often count to things far more than 1 million, far, far more than 1 million. So this is actually a relatively small amount of numbers to count to. And then we're going to, good morning. Then we're going to make a function that's just going to, it's actually going to run really fast, but we're going to call add slow. And it's going to equal an arrow function that doesn't accept any inputs. It's just going to run a block of code that, just simply declares a variable called s for summation that starts at 0, a variable called I that will be used to increment the loop And then it's gonna run a loop that starts from I equals 1. It goes less than or equal to the variable count 2. And then increments once each time. And it takes the value of I and it adds it on to the summation. So by the way, if you've learned a code similar to this, the plus equals operator just simply adds onto the previous value of sum. It adds that onto it. So it adds that amount onto it, whether it's 5 or 10 or whatever, it just adds that onto the variable s. Then it's going to return the sum. So that represents that line of code. Now, before I write any other code, let's just go ahead and show the result. Of course, you can't do anything in code without actually writing code to do it. Like you can't just make the code show you the result. So we're going to have to make a function called show result. So let's say show result equals, and it's going to accept a function and it's going to accept text to label the function with. And it's also going to be an arrow function that runs a block of code. This block of code is going to calculate the result. The result is going to equal, it's going to run the race, and it's going to put the function into it, and it's going to run the function 100 times. And then it's going to write to the document element. Now it's going to have a backslash x3c. Does anybody know what backslash x3c is doing? That's called an escape sequence or a character code sequence. That represents the beginning of an HTML tag. You should, because you're not supposed to have the opening tag of an HTML element inside of a script, because as the parser is parsing the HTML of the document, the script itself is not part of the HTML document. So if you have some tag opening up in the middle of the script, the HTML parser is going to think that is like some new HTML element being opened up, and it's really not. So that the x3c actually just means a less than sign. And then it's going to write the letter P, then greater than sign, which doesn't need to be escaped. Then it's going to say result for single quote plus text plus open is colon single quote. Just a second. And then plus result plus milliseconds. I'm going to put the milliseconds directly next to the result to add from 1 through plus from 1 through, I forgot to end the quote first, plus count 2 plus period. So there's that. And then I'm going to have it do show result add slow, and I'm going to call this an adding slow. I should say adding slowly, really, but because it's an adverb. Okay, let's just see real quick. So let's look through this code, make sure it all looks good to us. So fn is equal to this, equals that, count 2 equals this. There's that, s plus equals I, return s. Show result does this, runs the code. So there's that string plus the text plus that string plus that plus that string plus that plus that. Show result done slowly. Okay, there we go. Okay, let's see if it works. Let's open the JavaScript console and see if there's any hold on, let's see. Wait, do they have any more tools? More tools, there we go. Okay, perfect. Interesting. Oh, does anybody see a mistake that I just made, actually? It's not really a mistake. It's not a syntax mistake. I just put a line of code in the wrong spot. I put the function, I put the line that says the runs the show result function. I put that inside the function. So this line of code right here that's supposed to run the function is actually inside of this block of code that declared the function. So it's never going to run because the function won't run unless it gets called. And the line that calls it is actually written inside the function by accident. So if I put that line of code down there, now let's try it. Okay, so it only took 0.99 milliseconds to add the numbers from 1 through 1,000,000. So how does that sound? Does that sound good or bad? Pretty fast, right? Because a computer can do like I don't know exactly how many what processing speed this computer has, but it has a processor in it that can run like 2 billion calculations per second, right? So adding 1,000,000 numbers is really easy for it. In fact, it could add 1,000,000 numbers. It could add 1,000,000 numbers more than 1,000 times in just 1 second. So you might think, well, what's the point of doing this? What's the point of even knowing math if the computer can just add the numbers up easily by hand? Well, not really by hand, but that's actually the attitude of a lot of people. In fact, the vast majority of people who write code do a lot of code that is just very inefficient like that. But I want you to show how much faster it could be though if we did it another way. Let's go ahead and change the amount that it counts to. Let's try maybe 10 million. How long would it take to count to 10 million? Okay, well, it takes about 10 times as long. That makes sense. It takes 9.08 milliseconds to count to add up from 1 through 10 million. That's pretty cool. Okay, good job. Well, how fast do you think it's going to count from 1 through 10 million if we use the other option? The other way of doing it. Let's just try it out. So remember, this is the line of code that adds it slowly. Not the line of code, that's the block of code that adds it slowly. Let's do one that adds it fastly. So the line of code that adds it fastly is add fast. That's going to also just be an arrow function that runs. In fact, we don't even need a whole block of code for this. So we can just use an expression only. It's a single expression. So in order to add the numbers from 1 plus 2 all the way through the total count 2, all we have to do is remember the formula is n times n plus 1 divided by 2. So it's just that's n times n plus 1 divided by 2. That's all you have to do to count to the total with the mathematical way of doing it. So count 2 plus 1 divided by 2. So now we're going to run that code and compare it. So show result, add fast, adding fastly. I don't think that's really a word, but okay, ready? Let's do that. So it takes 0 milliseconds to add from 1 through 10 million using the fast way. So in fact, you could probably change this to 1 billion and it'd still take about 0 milliseconds to do it, but it'd take like 1,000 milliseconds to do this. So you basically have your code running like at least 1,000 times faster. And theoretically, this should eventually get to run at least 1 million or more times faster than that one does, because this algorithm right here, we're learning about algorithms later on in this course pretty soon, actually, in the next chapter, I think. This algorithm right here is an algorithm called an O(n) algorithm. That means it takes n steps to reach the goal. So it runs through a loop from 1 through n or whatever, and it does operations for every single step. So it takes n steps to calculate the total. This algorithm right here that does it is called an O(1) algorithm. It only takes one operation to calculate the total. Well, actually, it takes 3. But any constant amount that doesn't depend on n is still just rolled into the O(1). O means order of 1. It means any constant multiple of 1. So this basically takes one calculation, one line of code to calculate the answer. And so if possible, any algorithm that's an O(n) algorithm should be replaced with an O(1) algorithm if there is such a thing. And some algorithms, there isn't any O(n) algorithm that can do it, but there's some algorithms that there's an O natural log of n algorithm that can do it. So what's that talking about? So natural log is a function that calculates like the exponential power that would represent the same as a function. Like if you have 1,000, for example, if you have 1,000 steps to do, an O(n) algorithm would take 1,000 iterations to do it. So I'm going to say iterations. So each iteration might have 1 step or 2 steps or 3 steps, but an ON algorithm would take the same number of total iterations. It might take 3 steps for each one, but it would take that many loops to go through at the same number of steps that it would have to do for the total thing. So if like there's 1,000 steps to do, an algorithm would take 1,000 iterations to do all those steps. If you have 1,000 steps to do, an O natural log of n algorithm would only take 3 iterations. Well, let me change this to log, actually. Sounds better. So an O log n algorithm would only take 3 iterations to do it. Why is that? Because 1,000 is 10 to the power of 3. And an O1 algorithm, that's kind of like the Holy Grail. It would take how many iterations to do it? It would only take 1 iteration to do it, right? So if you got to millions and millions and billions of steps, then obviously this would go the slowest, this would go faster, and this would go the fastest. And there's some things that are even slower than that. Like image processing algorithms are usually ON squared or ON cubed, or maybe even worse, to do those types of things. So that was a pretty cool example of how something goes faster. Now I'm going to type in one more line of code to add the sum of maybe the n. And so what's something a little harder to do than just adding 1 through 100? What's something a little tougher than that? So let's give you another challenge. Ready? Challenge. Instead of doing 1 plus 2 plus 3 all the way through plus 100, what if you wanted to try this instead? 1 squared plus 2 squared plus 3 squared plus all the way through 100. 100 squared, my fault. So what do you think that would be? Do you think there's any shortcut for doing that? Well, you'd have to do, there probably is, you'd have to do a little bit of algebra first though. So, 938. I'll explain how to do it, but I don't think we have quite have enough time to solve all the equations. So, but what you could do is you could assume that there's a function called ax cubed plus bx squared plus cx plus a constant that would equal the correct answer. You just assume that. All right. Now what you do is you would assume that you'd assume a known value. So when x equals, let's just say when x equals 1, what's the correct answer when x equals 1? 1 squared is just 1, correct? So when n equals 1 or x equals 1, the correct answer equals 1 because 1 squared is 1. When you add up the first 2 numbers, squaring each one, what's 1 squared plus 2 squared? 5. You're right. That's correct. And then when x equals 3, what is 1 squared plus 2 squared plus 3 squared? Right. So this actually gives you a system of 3 equations. We only need 1 more actually to finish it. When x equals 4, what's the correct answer? What's 1 squared plus 2 squared plus 3 squared plus 4 squared? 30. Okay, 30. Correct answer equals 30. So I won't be able to solve them, but basically you could take this equation, which you know, ax cubed plus bx squared plus cx plus d is the correct answer, and you'll get a system of 4 equations. I'm going to actually, so can anybody remember those numbers 1, 5, 14, and 30? I bet you we can have we can have an equation solver online solve this for us. So let me look right here real quick. Equation system solver. Ready? So equation 1 is going to be x equals 1. So it just be a plus B plus, let me zoom in a little bit so you can see it better. The first equation would be A plus B plus C plus D equals, we said the total was 1, right? If I plug in 1 for X, it'd be A times 1 cubed plus A times 1 squared and so forth. So for X, for the X values, I'm plugging 1 in, which gives me 1A plus 1B plus 1C plus 1D plus 1 and so forth. Now I'm going to plug in 2 for X. So what's 2 cubed? 8. So you'd have 8A plus, and what's 2 squared? 4B plus 2C plus D. The total was supposed to be 5 for that one, right? Now let's plug in 3 for X. What is 3 cubed? 27. So it'd be 27A plus 14. No, sorry, my fault. Plus 9B plus 3C plus D equals 14, right? And then what is, let's go to 4. What is 4 cubed? 64, right? So 64A plus 16B plus 4C plus D equals 30. Let's see if that can be solved. Okay, let's see. So according to this, it can be solved by the numbers 1/3. So the equation is 1/3 X cubed plus 1/2 X squared plus 1/6 X plus 0. So let's put that line of code into our problem, into our code real quick. So the answer is this. So the solution basically is that 1/3 times X cubed plus 1/2 times X squared plus 1/6 times X plus 0 equals the correct answer. And let's just, in fact, that can be factored. I already know what it can be factored into. It can be factored as being X times X plus 1 times 2X plus 1 divided by 6. If you get a common denominator and factor it all out, it can be factored like that. Let's test that formula out real quick and see if it actually works. By plugging in 4 and just checking if we really get 30. So if I plug in 4 for that, what's 4 times 4 plus 1? Be 4 times 5, right? And what's 2 times 4 plus 1? That'd be 9, right? So what's 4 times 5? So I'm checking the answer for X equals 4, right? So what's 4 times 5 times 9 divided by 6? That would be, let's think. So that'd be 180 divided by 6. That'd be 30, I think, right? So that would be 30. That does work, actually. So that equals 30. So that formula works. So now let's program that. Let's program that one into the program that one into here. So we're gonna say add slow 2. So watch carefully what I'm doing, because you're gonna have to do one more like this. You're gonna, so just copy the function that says add slow and change the name to be add slow 2 or add slow 3 or whatever it's called. And the difference is, instead of adding I each time, you're gonna add I times I. So the operator to the power operator means something different in this computer language. You can't say I to the power 2 like that. You can do I times I. That'll work. So that basically adds I squared each time. And then the add fast version 2 is going to take the formula count 2 times count 2 plus 1 times 2 times count 2 n times n plus 1 times 2n plus 1 divided by 6, right? So now let's change this line of code and change this to say add slow 2 and add fast 2. Ready? So we saved that. Let's go back to this page. If I even have it up here anymore. Okay, so now it runs it in 9 milliseconds. This one still goes in 0 milliseconds. Let me refresh it just to make sure it's running the new code. Yep, it still takes 9 milliseconds. Now this one actually took 0.01 milliseconds. But still, that's 900 times faster. So that's pretty cool. Okay, so your challenge is, I'm going to tell you the formula actually even, but you just have to add, you have to copy this code. I'll give you the code even, you copy all the code, and you just have to add one more function called add slow and add fast 3. So just like I said, add slow 2 equals this, and add fast 2 equals this. You're going to copy this code and change it to be add slow 3. So you're not going to delete the old one, you're just going to copy onto it. And your formula that you're going to have to do is the formula for the cubes of the numbers. So 1 cubed plus 2 cubed plus 3 cubed plus all the way through 100 cubed or whatever, or any number cubed. The way to get that is equal to this. You take the number n equals the final number being cubed from 1 through n. Whoops, it did some auto completion thing. So with the final number being cubed from 1 through n is called n, the formula for it is actually n times n plus 1 divided by 2. Does that look familiar? That's the same formula we used at first. If you just square that formula, if you simply square that formula, you'll actually get the final answer. So let me show you how you can do that. You can actually use the same exact formula as before. Well, anyway, I guess I'll let you figure it out. But remember, you can't use the square key though when you type this code. So you're gonna have to write that like this. So you're gonna have to say n times n minus 1 times that, like that, when you do your code. So that's the formula for calculating the sum of the cubes. So you're gonna make a function called add slow 3 and say I times I times I. You're gonna add the third power. So it's I times I times I. And then you're gonna add a function called add fast 3 that instead of calculating this formula right there, it's gonna calculate that formula right there. And you'll have to use the variable count too, instead of the variable n. But otherwise, other than that, it's gonna say it like that. Any questions? So let me go ahead and make sure I call out attendance another time or two. I mean, not another time or two, just another time. Amani, you're here now, right? Okay, perfect. LaShawn. Perfect. Shamarius, Anthony, Phoebus, Anthony Johnson though, right? Okay, Anthony Johnson. Colin Morrison. What about Ignacio or Caleb? Caleb, are you here? Yeah. Okay, perfect. And then Arturo, here, okay. So I'm gonna put all this code into Moodle. You can download it all. And I'll see you again next time. Any questions? Yes, I'm gonna make the due date be 11:59 p.m. instead of 9:00 a.m. Just so that the online people, maybe if they're at work, they won't have such a hard time. Thank you very much.
You want the stuff you, it's like,
Oh, the stuff oh yeah, and by the way, I have everybody who turned it in on paper, I have your assignments from last time. And also if you have the next one, yeah, you can turn that in as well.
oh,
Hold on a second. Yeah. Yeah, and this is not the way that I wanted you to do to it, but it was still like, oh, in the future, make sure that you do it the way that like reads like that out. Yeah, like this, like that. The accent on to the outside, so forth. Okay. Yeah, okay, and then yours, if you turn it on paper.
No, I think I did.
Okay. Okay, yeah.
But I did.
And then you can try to resubmit this if you want to, but you just said that this is element of the left and element of the right, but there has to be like you have to explain like why, like which one it's a part of, for example, like it's a X being on the left side, and then like therefore like it's a part of that or whatever like that, but that makes sense. So like,
how did they explain it?
so you have to say, let X be an element of like one side or the other side, it could be either one. If X is an element of this side, then that means that either X could be an element of this one or it could be an element of this one or whatever. But either way, it's an element of A, right? And then And then that proves it's an element of A. So basically you're checking an element of this side, and you're proving that it's an element of the right. And then you let X be an element of the right, and that's an element of the right, then it either has to be an element of. So if that, so that's an element of the right side, then there's two cases to consider, if it's part of B or if it's not part of B. If it is part of B, then it's gonna be an element of this union. If it's not part of B, it's whatever, like basically you just consider all the different cases. And then, if that makes sense. You can always ask me about it in my office or anything like that. That's all. It's easy, and you don't have to do it exactly like this. Like, yeah, basically like, if you, just do your best, and you could even try, like, I let one person just draw like a Venn diagram. But it was, because it was logical, but it wasn't really great, but I told him that he could do it next time, but since I let him do it. This time I could also possibly let you do it as well. And here's your, you actually have it right, if you just forgot the other half, you said 25%, so. It doesn't exactly have the same effect, reading slide, we get the other side. So just make sure that you write out the other direction as well.
Did I redo this? Like,
Yeah, you can
I-
you can have the other part, yeah. Because effects is in the left side, we did that part, but then you have to say that what effects is in the right side, what effects is in element of A. Then you have to prove that it's also an element of the left side. That's
Okay.
all. You're welcome.
Did mine submit? I turned it online.
I have not checked actually the online, yeah,
Okay,
yeah, but I'm gonna check those now, well,
okay.
thank you very much.
So I have a question.
Yes.
So if it's one per, I mean, 1-to-1, is it
Yeah.
bijection like automatically?
No, if it's 1-to-1, that means it's an injection. So if it's like a line like y equals x, that's an injection, but it's not always a bijection. So the function y equals x happens to be an injection as well as it goes from the bottom to the top of all real numbers. So it's also a surjection. So if it covers the whole entire like range from -infinity to infinity, then it's a surjection. But it's not necessarily a surjection just because it's an injection, or so if it's 1-to-1, it's not necessarily, so like, for example, the function y equals e to the x, it looks like this, right? That's 1-to-1 because it always continues curving up, but it never is negative though. So it doesn't cover all real numbers. So it's an injection, it's 1-to-1, but it's not a bijection because it doesn't cover all, the y values don't cover everything.
Cause I thought that we were, the questions on, 22, I mean, the problem 22,
Yeah.
the questions. I thought that it was either not a bijection or, cause